So the circuit that we are building here has a 7414 IC, which is the IC all the way to the left on the proto board here, that has a Schmidt trigger based inverter. There are actually 6 of them inside this. We only need one of them. That's the 7414 chip. And next to that, right in the middle of the proto board, we have a 74393 chip. That is a 4-bit counter. So we were talking about a 3-bit counter counting from 000 all the way to 111. This is a 4-bit counter. So it counts from 0000 all the way to 1111. So in decimal, it is actually counting from decimal 0 to decimal 15, a total of 16 counts, and then back to 0000. So that's what it's doing. The outputs of the 4-bit counter are available on pin 3, pin 4, pin 5, and pin 6. Those are connected to 4 light emitting diodes, D1, D2, D3, D4. The negative side of those diodes, which are essentially the shorter leads, are connected to resistors R1, R2, R3, R4 and connected to ground. So whenever we have a QA going from 0 to 1, LED D1 should go from off to on. So if it is blinking, that shows me that the counter is counting. So um, that's how I've set up the circuit over here. Now, a few things that a lot of students get it wrong when they wire this circuit is this. The way I have connected the 4 LEDs, I have staggered them in terms of the pins. And so, for example, the long leads are the positive terminals of the light emitting diodes. Those in the schematic look like the triangles. So there's a triangle and then there is a flat side. The flat side is the negative, the triangle is the positive. The positive has the long lead. So the long leads are going to pin 3, 4, 5, and 6. So the only things that are connected to that particular row are the positive terminals of each of those red LEDs here. The negative side of those LEDs have a separate independent row here. So there, and there. So those 4 are the negative side, and I've connected the 4 resistors to those negative side of the LEDs, and the other end of those 4 resistors is connected to ground here. Now this circuit is slightly different from usually how I build circuits. When I build circuits on proto boards, I usually have one of the rails on the top. Usually I will have a power rail, which means say 5 volts, and on the bottom I may have a ground rail. But just to keep this circuit a little bit pretty, what I did was I have both top and bottom being used as ground terminal. There are only 2 places where I need plus 5 volts. Those are the pin number 14 of each of these chips, 7414 and the 74393, the 4-bit counter. So I've connected the red wire from analog discovery to pin 14 here. Then I've used a wire to jump that voltage to pin number 14 over there. So that's how I have connected the pin number 14s. Pin number 7 goes to ground here and here. So that's as usual. And I have connected the input here. If I look to the circuit diagram, I have input of the 7414 chip coming from the wave generator AWG1, wave gen 1. So that is my yellow wire from the analog discovery. Let me just connect that to the yellow wire here of analog discovery, and we are ready. And I've also put an orange wire, the channel 1 plus, to this to see that waveform that I'm generating on the oscilloscope. So that's my orange wire for that, which is so yellow and orange. I'm giving the input to the inverter, and I'm also measuring it at the same time. So for this chip, the clear is active high. That is exactly correct, Derek. The clear, which is pin number 2, is an active high input in this case, different from what we had earlier with the JK flip-flop. And we know that because you see this, the clear input that is shown on pin number 2, there's no bar or there's no bubble on top of that, which indicates that it is an active high input, so a normal input. So if you want to clear it, you have to connect it to 1. If you don't want to clear the flip-flop, what counter, then you have to connect it to ground. What does clearing the counter mean? It means that I will have all the outputs go to 0000 and it will stay there. I don't want that. I want this counter to count from 0 to 15 in decimal. So I will not clear it. And the way I don't clear it is by connecting pin number 2 to ground. And that's what I did over here in the circuit board. I've connected pin number 2 of the 74393 chip using this black wire here connected to the ground terminal there. Okay, so we've talked about those grounds. This purple wire over here is essentially taking the output of the inverter chip and giving it to the clock input of the 393 chip. So there's a wave gen, perhaps a square wave, which gets inverted first through the 7414 chip, and then it acts like the clock input or the count input for the counter chip. Now, an interesting question here is, why did we invert this? Why couldn't we have just gone from the square wave directly into the clock input? We could have done that. If we do that, then we have a negative edge triggered 4-bit counter. But if I put a NOT gate in front of this, I effectively have a positive edge triggered 4-bit counter in this case. So the counter is going to respond to the positive edges of my wave gen instead of negative edges because I have an inverter in front of it. So that's the only reason why. Okay. Another important question over here is, why do we need those 220 ohm resistors? Well, those resistors are essentially protecting the 4 LEDs. So for example, if you have pin 3, the output QA from the counter as 5 volts, it may damage the IC. Sorry, it may damage the LED because that's too much voltage for it to turn on. The red LED usually turns on between 1.5 and 2 volts. That's enough for it to turn on. And if we give it 5 volts, that's too much. So it may damage the LED. So we need to split it up between two components so that each component gets a smaller voltage. So by using the principle of voltage division, if we have a 220 ohm resistor in series with LED, the voltage available at QA, QB, QC, QD will be split between those two components. So for example, if I wanted to dim the LEDs, I only need to increase the resistors R1, R2, R3, R4 to a higher value. So that's how it's playing a role there. So let's hook it up. Let's see how it responds. I'm going to connect the red wire here to plus 5 volts, so red wire from the analog discovery, and I'm going to connect the black wire here to the black wire of analog discovery to make the ground connection. And as you can see, I have used a black wire to connect both the power and the ground rails. Well, in this case, both are ground rails. So I've connected them together using a black wire. Okay, so what do I need to do? I need to first turn on supplies. So let's turn on the 5-volt supply. Right now it is turned on. Next, I need the wave gen, and wave gen in the write-up is a frequency of 20 hertz, and the voltage should go from 0 to 4 volts. It's a square wave that goes from 0 to 4 volts at a frequency of 20 hertz. So I can set that up in wave gen Type is going to be square wave. Amplitude, so if I need 0 to 4 volts, then amplitude needs to be 2 volts. If amplitude is 2 volts, that I get a peak to peak of 4 volts, I need to push it up by 2 volts. So I'm going to make the offset as well 2 volts. So I have an amplitude of 2, an offset of 2, which gives me uh, a square wave between 0 and 4. I only need to change the frequency now. Frequency needs to be set to 20 hertz, which is right there. Okay, so I've set up my wave gen exactly the same way as the experiment write-up needs me to set it as. I will start it, and voila. I hope you guys can see that the LEDs have started blinking. They're actually counting 0000 all the way to 1111. Um, One question that we can ask at this point is, did they start counting at 0000? Well, the answer is no. That they didn't start at 0000. They started at some arbitrary starting point, and then they started counting from there. They went to they went to 1111, then they came back to 0000, and then they kept in the loop. If we wanted to specifically start at 0000, we can only do that by using that clear input, connect it to 1, connect it back to 0, and then start the counter, which we didn't do here. So we just arbitrarily started at some arbitrary count value and then started counting from there. So the LEDs are right now blinking too fast. It doesn't make too much sense. So what I'll do is I'll slow it down so that we can count in binary with it. So I've made the frequency 1 hertz, 0, 1, 2, 3, 4, 5, 6, 7, 8, and you can keep going. So right now you can see that the LEDs are counting from 0 to 1 to 2 to 3 and 4 and 5, and I think you can relate that to the decimal values now. So the least significant in this is the topmost LED, that's the QA. So in our case it is Q0. It's the topmost LED is the least significant, and the bottommost LED changes the slowest. So that's the most significant, QD or Q3 in our conversation. Now this particular part also requires me to observe the clock signal and QA, then clock with QB, clock with QC, and clock with QD. So what I'll do is I will start the scope. So far, no, not scope, with scope, and I already connected the orange wire. So I'm going to make a few more connections. Let's say I have orange stripe. I'm going to connect that to ground. Orange stripe connected to ground. That completes the orange stripe. Then I have blue stripe for channel 2. Blue stripe also needs to go to ground, so that connection is also made now. And blue, uh, let's say we start with the least significant first. So if I start with the least significant, I'm going to put this blue channel on pin number 3 of the 74393 chip right there. So I've connected orange, blue stripe to ground, orange stripe to ground. So I'm measuring clock on channel 1, and right now I'm measuring QA on channel 2. So let's start the scope. If I start the scope, and so what is happening right now is things are changing very fast. I'm going to have to slow things down. So I will change the time base to 200 milliseconds per division. It looks like that is too slow. So what I'll do is also change the range to be 1 volt per division so that I zoom out in terms of voltage. I will turn off the noise on both the channels next. I will increase the plot width to say for example 3. Right away I hope you see that the blue line goes up when there is a positive edge on the clock. So we took a negative edge triggered counter and we made it into a positive edge triggered counter by putting a NOT gate in front of it. Let's see. I need to look at 50 cycles of the clock as per the experiment. So I'm going to have to look at a lot of time. So if I do this, I have few more 2 seconds perhaps. 2 seconds is oh, I see. My frequency is too slow. I need this to be 20 hertz. So I'm going to go back, change it to 20 hertz because that's what we are expected to do. Come back to scope and it is now too much. So let's go back and look at this is plenty. This is actually 100 pulses almost. So 250 milliseconds per division actually should give me 50 clock cycles over here. I'm going to also play with the offset a little bit so that I have it centered around 0. So change that and change that. Sorry, both of these should be -2 and -2. All right. So that's what we have. We have orange showing clock and blue showing QA right now. And every time I move the blue channel up 1 bit, so for example if I go from pin 3 to pin 4 to pin 5 to pin 6, the frequency of the blue line should get half and half of that, half of that, half of that. So if I have the clock frequency as 20 hertz, QA is repeating at 10 hertz, QB should repeat at 5 hertz, QC should repeat at 2.5 hertz, and QD should repeat at 1.25 hertz. And we can take a look at that very easily by simply moving the channel 2 pin to pin 4, 5 and 6. And in waveforms you should expect the frequency to get slower and slower and slower. So I'm moving one level up and you can see that the frequency slowed down a bit. In fact it got halved. If I move it one level up further, it got slow by half again. And the fourth most significant bit, it got slower again. Now when you look at this plot, I hope the 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 reasoning for looking at 50 clock cycles is very clear now. See, when you didn't change the clock, you just looked at the same clock 50 cycles, and we have kept cycling through the outputs q3 q0, q1, q2, q3. And that's how we build a that's how we are exploring this 4-bit counter using the chip 74393. Okay, so I've recorded these plots and I have uh, provided them for your use on Piazza. So please feel free to download them and analyze them. But I think this is it for the discussion on the 4-bit counter, part C, experiment 7. So let me stop the recording here so that